Hello and thank you for attending my talk. I am Daniel Sigalov and I'll discuss an improved algorithm for universal sensor registration. This is a joint work with Aaron Gal, Boaz Victor. The outline of the talk is as follows. I'll give some brief introduction to the subject, state the problem, describe some derivation details, and conclude with numerical example summary and some ideas for future work. So we are dealing with the problem of sensor registration, and we consider a set of S sensors, which may be either 3 or 2-dimensional. In the former case, the sensors deliver range, azimuth, and elevation information, while in the second case, the sensors deliver only azimuth and elevation data. Each sensor is assumed to be associated with an unknown rotation matrix AS, such that any vector represented in the coordinate system of that sensor is rotated by that matrix. For example, in the situation depicted here at the bottom of the slide, the blue line represents the true target, and there are two sensors having rotational bias psi1 and psi2. The sensor on the left rotates the actual target by the angle psi1, thus creating the yellow line denoted here as rotated track 1. The sensor on the right rotates the target by the angle psi2 and resulting in the red line, which is the rotated track 2. Both angles are unknown, and our goal would be to estimate the psi1 and psi2 angles using only the red and yellow lines that are shown here. We use targets of opportunity, which are a set of noisy detections observed by the sensors, and we do not assume any dynamical model that is obeyed by the target. We make few additional simplifying assumptions. Specifically, we assume that the sensor locations are known, that the data association issue is taken care of, and that the time synchronization problem is solved. Our goal would be estimating the rotation matrices of all sensors, and there are a few questions we may ask to make the problem interesting. First, is it even possible to estimate all the rotation matrices of all the sensors without having some reference? The second question is, assume we have some solution, is it a unique solution? We'll address partially these questions in the sequel. So to illustrate the situation, consider the setup depicted here. We have a set of 8 sensors ordered on some circle and numbered from 1 through 8. The actual target is shown in blue in the middle, and each sensor rotates that trajectory by some rotational matrix, which is unknown. Some of these rotated versions are presented here. So our goal would be to estimate the rotation matrices, thus bringing all the rotated trajectories to the common place. To state the problem, we consider a simple case of 3 sensors, which measure n Cartesian positions of the target. These positions are denoted as TIs, and we denote by X, Y, and Z the measurements of all sensors. For example, sensor number 1 has a rotational bias represented by the rotation matrix A, and its measurements are A times the difference between the actual ground truth Ti minus the sensor location L1. This measurement is noisy, and the noise is represented by the vector Vxi. The same goes for sensors 2 and 3. However, they have rotational biases represented by the matrices B and C. All the matrices A, B, and C, as well as the set of TIs, are unknowns. We take the maximum likelihood approach and seek for the estimation of those unknowns. Assuming Gaussian noises, the objective becomes the following sum, where each element is a squared norm of the distance between the measurement of the sensor and the rotated version of the ground truth. If we look at the case of S sensors and N measurements, then we have the objective, which takes the following form. It is a double summation, where the first summation runs over the sensors, and the second summation runs over all the data of each sensor. Each element in the summation is the squared norm of the difference of the sensor readings and the rotated version of the ground truth. This is a constrained optimization problem, since A1 through AS are assumed to be rotational matrices, which are orthogonal matrices with determinant 1. Since this is a hard optimization problem, we propose an approximate solution, which I'll describe next. So looking at the objective once again, we make 2 simple observations. First, fixing Ti at some given values, it is easy to optimize for AS. In fact, in this case, the problem becomes a set of separate problems for estimating each individual AS, And this can be done by using some standard algorithm for solving the known Waaba problem. The second observation is that fixing all the rotational matrices, it is very easy to optimize for TI. We thus obtain the following iterative procedure. We use some values for TI and optimize for AS, and then use those values for AS and optimize for TI. We repeat the procedure until some convergence criteria are met. So how do we find those positions, those Cartesian positions, which we use in the objective? Well, in the case of three-dimensional sensors, these are obtained trivially by converting the spherical measurements, range, azimuth, elevation of each sensor into Cartesian positions x, y, z. Thus, we may use the algorithm, as it was shown in the previous slide, solving the Waaba problem for each AS and solving some simple least squares problem for finding TI. It is very easy to see that in this case, the sequence of costs generated by the algorithm converges. Thus, the algorithm halts. In the next animation, we'll show a simple visualization of how the algorithm works for the case of 3D sensors. So here we have a set of 3 sensors, each rotated by its own rotational matrix, and the ground truth trajectory here shown in blue. We run the algorithm and we see that the sequence of trajectories generated at the end of each iteration converges pretty quickly to the actual ground truth. Our next step is the calibration of two-dimensional sensors. In this case, it seems that the positions, Cartesian positions that are needed in the algorithm are missing since we only have access to azimuth and elevation measurements. However, using 2 or more sensors, we can triangulate the direction vectors and obtain Cartesian positions from which it is easy to obtain the missing ranges. This is depicted here. Using 2 or more direction vectors, we may find the triangulation point when solving a simple nonlinear least squares problem. A question that may be asked is how do we do triangulation when our data is misaligned? Well, we can add additional step in our iteration such that the computation of the rotation matrices and the computation of the estimates of the ground truth are augmented by the triangulation step. So the whole scheme now looks as follows. We perform triangulation of the direction measurements and compute range estimates. From these, we compute 3-dimensional positions that are needed in our optimization. And then we perform the 2 steps from the previous case of 3-dimensional sensors to estimate rotation matrices and the ground truth. The whole procedure may be demonstrated in the following animation, which follows the same setup as in the case of 3-dimensional sensors. So we have 4 sensors in this case, and the result of each iteration is shown here. It can be seen that the result converges to the actual ground truth. It may be seen that at the beginning, the trajectories that are generated undergo deformation. This is because the initial triangulations are based on misaligned sensors. Now let's compare the present algorithm with another one that we presented here at the conference 2 years ago, in which case we try to minimize the differences between every 2 sensors. That algorithm was shown to achieve nice performance. However, the minimization, the optimization depended on the order of the sensors. So there are cases in which for some specific orders, the algorithm failed to converge. As an example, this is going to be shown now. So the old algorithm reached a local minima, at which it alternated between 2 solutions, thus failing to converge. However, the algorithm represented now is indifferent to the order of the sensors and converges for any initial conditions when dealing with 3-dimensional sensors. So let's consider some results on the performance, single run results for some misaligned scenarios. When we run the algorithm, the biases are estimated, and the initial biases of 10 degrees ended in estimates of up to a third point after the decimal point, third degree after the decimal point for each angle. We can perform some Monte Carlo analysis in which we compute the overall estimation error in milliradians versus number of sensors. It is readily seen that starting with errors of about 90 milliradians, we end up with as low errors of 3 or 4 milliradians. And it can be seen that the estimation accuracy in the psi direction is significantly better than in theta and phi. This happens because of the geometry of the scenario. So let's summarize this talk. We presented a calibration algorithm to calibrate angular misalignment of 2 or 3-dimensional sensors without having access to any reference. We showed that the algorithm converges for the case of 3D sensors. The method is free of tuning parameters and does not require any target model. There are some directions to be considered in the future. We'd like to look at mixed scenarios with 2 and 3-dimensional sensors. We would like to analyze convergence for 2-dimensional sensors and investigate the dependence on sensor target geometry. An additional item that is interesting to look at is the introduction of covariance matrices of the sensors into the objective. This is an interesting and non-trivial problem. Any correspondence or questions that you may have are welcome. Please send them to one of these emails. Thank you.